to introduce you to some friends of mine that may not be as visible within the AGI and OpenCog development space to the community. So I'm super excited to share their projects, what they're working on, and some of these really interesting elements of bringing OpenCog to agents. Interacting in the real world, solving, or not in the real world, agents interacting with worlds and solving problems, solving goals. So I'm super excited to introduce Barrett Cook. He's an AI developer for SingularityNET, and he's going to introduce us to the AIRIS project. And Patrick Hammer, who's a postdoc at KTH, and Peter Esave, who's a PhD at Temple. And they're both collaborating with the OpenCog team on AGI development and meta development, and have just a very collaborative approach with everything that we're doing, and forming a foundational outreach for different types of development, working on NARS, Metanars, and NACE, which we'll get an introduction to today. So today we're diving into experiential learning, one of the most exciting areas, the most demonstrative areas of OpenCog development. And we won't get a chance to dive into the ROCCA, the rational open controlled agents for SingularityNET today. Nil and Hedra couldn't join today, but we'll have a part 2 where we'll dive into more of that. And first, I'd like to kick off discussion with Barrick, Patrick, Peter, on what is experiential learning. So who would like to give their view on that first?
All right, I'll chime in for that. So the idea behind experiential learning is making agents that adapt and learn from interacting with environments. It's kind of how we consider embodiment in AI. And so these kind of agents interact with the environment, experiment with it, learn how the environment works, and then can use that knowledge to make decisions, make plans, solve problems, or do tasks in an environment.
Fantastic, thanks.
And I would like to add to this that since in artificial intelligence there's this main paradigm of reinforcement learning, but what is not usually captured well in reinforcement learning is the presence of causal relationships, which the agent has to figure out, which allow it to plan ahead and reach different goals. So it's not just about a single objective function or single utility function. It's also that the agent actually should gain kind of a representation which allows it to understand how the environment around it works so that it can achieve different objectives.
And also how to update whatever it learns in the real time. That's also important. Not to repeat the same mistakes, ideally twice, but it doesn't happen in the AI world. That's the most important. Estimate uncertainty, take uncertainty into the account that nothing is certain. Those are the key things for the experiential learning in the real time.
Awesome, thank you. Yeah, I recall Alexei did a demo a little bit back with a Minecraft agent, and one of the things he was able to show was that the agent was able to learn on a first pass that if you touch the cacti in Minecraft, you die, right? Where a neural symbolic reinforcement learning, it has to die and die and die and die before it learns that relationship, or the probabilistically don't touch the cactus, right? Where in Minecraft you can tolerate some of that, but for instance, in a self-driving car, you don't even want it to learn once, right? You want it to have that causal relationship immediately on very dangerous situations, and being able to update in real time and in the real world about what's happening. This becomes very critical for agents interacting in the real world in critical senses. So we've looked a little bit at what these agents are looking to do. Can you talk a little bit about some of the applications of having these types of experiential learning agents running with proto-AGI or AGI eventually, but advanced AI systems at least.
Yeah, so the idea with this is to be able to have systems that don't require millions and millions of training sessions to be able to learn how to do a particular task, and also to be able to adapt to unexpected things that it may encounter or unexpected locations. Because that's one of the big problems with reinforcement learning, is that you can train it a whole bunch on a particular set of data or like a particular environment. But if too much is different in that environment, then it breaks down and it's not able to adapt to those changes. And so we really want to be able to introduce an AI system that can adapt to that kind of difference and experiment and learn how those changes in its environment affect its planning or what it may be planning to do, or don't affect it at all. And so it will be able to learn very, very quickly, like you were saying, Haley, about the environment around it. It won't have to sit and smack its head against the table 100 times before it realizes that there's a table in the way. And systems like that will be able to operate in much more dynamic environments, and possibly even in real world robotics, which is kind of the end goal.
And that's also where we have been focusing on. Actually, we have a publication for ACRA 2024, where we essentially apply non-axiomatic reasoning system on a mobile robot and let it carry out a garbage collection in the city of Aarhus in Denmark. And what we can essentially show is that this kind of real-time learning capability is really beneficial to increase the robustness of the overall solution, because it will be way more robust to disturbances which can occur at random.
Right. Yeah, and we will guide you during the presentation about that project a little bit. Show the video, a demo.
That's fantastic. And the community, please feel invited to dive also into the blog post we had on SingulariNET's progress towards beneficial AGI in 2023. It lays a great foundation for everything we'll talk about here. It has a couple of the demos in there, and then of course we'll cover them today. But it's a great foundational knowledge for everything that we're talking about here. And I appreciate, again, everybody being here to discuss this, and the excitement and enthusiasm for participating in this development process. So with that intro, I know that we have a lot to cover today, a lot of very cool projects. I'd love to hand over to Barrick and discuss your AIRIS system.
All right. Well, I will go ahead and do a quick screen share here, as long as all of that still works like we hoped. There we go. Okay. So this is just an overview of the AIRIS project. It's a causality-based approach to machine learning, like what we were talking about. I'm going to run through this quickly so that I don't take up all of our time, but there's more details in other videos that are in the stream's description, and also GitHub links if you want to dive in a little bit deeper. So the overall idea of this is that when we humans are writing code, we're primarily using if-then rules. So if I were to code a simple puzzle game, I might do something like, if the cell next to the bot is empty and the action is move left, then move the bot to the left. But what if an AI agent could learn those rules automatically? And could we see it have the same intelligent behavior that we can manually code into these systems? And how can an AI even learn these rules? So if we look at what values change from one state to the next, then we can find everything that an AI would need to be able to learn these types of rules. So for example, here's what we need to model, the little agent moving to the left. Here's our example rule that we would code. And here is an example of what the AI would be able to infer from this kind of observation. So if the bot is the cell and the cell next to the bot is empty and the action is left, then the bot is going to turn into an empty cell. And likewise, if the cell next to a bot is empty and the action is left, then the empty cell will turn into a bot. So we get two rules, one that changes the bot into an empty space and one that changes the empty space into a bot. And if we combine these two outcomes together, then we get the little robot moving left. Now, once we have some rules, we can start using these rules to make predictions about how the world will change when an action is performed. And if we chain these predictions together into a state graph, then we get an agent with an internal world model that it can use to make plans. So from the current state, it moves left and we get state 1, and then state 2, and so on and so forth. But if you notice here at the last state, it's got a bad prediction because it hasn't observed moving against a wall before. But because the wall is different than an empty space, its prediction confidence of that interaction is lower. And we can use that lack of confidence to guide the agent towards novelty where it can learn new rules. So when it does encounter a wall, it creates new rules that say, okay, well, nothing changes. I just end up sitting in the same space. And if it encounters a battery or other object, as in this example, and its score goes up, it notices that change too. That, hey, if I moved left on there, right next to a battery, my score goes up. Then we can start giving it objectives and goals. We can say, okay, we want you to increase your score. And if we give it that kind of an objective, it will build out a state graph larger and larger until it finds a result of it collecting a battery and it's increasing its score. Then all it has to do is trace through that state graph, the action sequence, perform those actions, and achieve whatever we want it to achieve. Now, as the complexity of the task grows, that kind of breadth-first searching becomes very, very inefficient. And so that is where something called the dynamically calculated goal heuristic comes in. So this is a value that the system automatically creates from its rules that tell it how far or close it is from a goal. So it takes a rule that it has learned from its rule base and says, okay, this results in my score increasing. Either I need a battery to be next to the bot, which is 5 squares away, or I need the bot to be next to the battery, which is also 5 squares away. So that value 5 is then fed back to the planning algorithm to tell it how close or far a predicted state is. So if it performs an action and that value goes up to 6, it knows that particular action takes it further away from its goal. And likewise, if it moves closer, that value will drop to 4. But the cool thing about this is that it allows us to change the goal of the agent at any time. Because if we change the goal to, okay, now decrease your score, go jump in a fire. So all it has to do is perform that exact same type of calculation to tell it how far away it is from achieving that particular goal, and it will just guide its way towards that outcome. So you can kind of think of these calculations as unconnected goal substates that are floating around in the state graph. And this is what that looks like. So we're going to do a quick example here of how this state graph works. So we have a state like this, and we're going to call that our starting state of state 0. And we have a bunch of these unconnected goal substates over here. And that's all the different spots that the system knows that the agent or the bot has to be in order to perform this action and complete the goal. And some of those are not possible, but that doesn't really matter to it. It's just trying to figure out a way to get there. And so from the initial state, it's going to start making predictions. And let's say it tries to move left. From this, it creates a prediction and connects those two states together, state 1 and state 0, with an edge. And that edge is labeled with the action that was performed, the confidence of that prediction, and the goal heuristic value that that state was analyzed to have. So in this case, it's 1, 2, 3 blocks, 1, 2, 3 blocks. No matter which way you go, it's 3 blocks away from the goal. And let's say it also tries to move up. And it hasn't interacted with arrows before, so its confidence is lower. It's only 0.75%. But we're going to store that in state 2. It's going to continue predicting out and building its state graph. So it's going to predict, okay, this is what down does. This is what up will do. But when it reaches back to this state 2, because that was a low prediction, it's not certain that that is the actual outcome of what that interaction is going to be. So it doesn't keep predicting out from there because it can hallucinate all kinds of crazy things. But from these couple of states that it has generated, state 3 and state 4, it's looking to see, okay, which one is closest? Which one has a better heuristic? It's like, okay, state 3 has a lower one, and state 4 is better. So we're going to go with state 4, and we're going to make a couple more states, moving left and moving up from there. And both of these have the same heuristic, because if you notice, that one is only one space away, and that one is only one possible space away. So both of those are valid, and it'll keep building out from there. And it'll just keep building a larger and larger branching state space. So it moves left, sees that's further away. It moves up against the wall. Well, that's just the same state. It doesn't go anywhere. But here, the result of moving up matches one of the goal substates exactly. And so it says, okay, that's it. That's where I need to be. And I can perform that action and achieve my goal. And then it just traces back from the beginning and performs the sequence of actions through the state graph that lead towards its goal. So it's very similar to the way that we program like good old-fashioned AI in video games and telling the AI agents in video games what to do by searching a state graph of actions and performing those actions in sequence. So I've tested this in a couple different environments. MNIST, which is the handwritten character benchmark. It's a pretty standard benchmark. The cart poll, which is a environment where the agent has to balance a pole on top of a moving cart in a physics-based environment, which could be a good benchmark for like robotics applications and whatnot, and my Grid World puzzle game. Now, MNIST is kind of weird because it's not really any planning, it's just pure prediction. Agent is shown an image, blank label, has to predict what the label will be, and then it's shown what the correct label is to compare its prediction against. And the conditions of these rules are all the pixel values of all the characters that it is exposed to. And the results are pretty good. So in a first run through of the MNIST training of 60,000 handwritten characters, its accuracy rises very sharply, and it ends at about 91%. And then when it's dropped into a fresh set of 10,000 characters, it starts at 100%, but quickly drops down to 93, and with a low of 89, and ending at 93%. Now, if I put it back into the training set, it hovers right around 98% accuracy. So these are very, very good results very quickly. Compared to a paper in 2022 that used an optimized deep learning for MNIST, it took about 100 training iterations to have the same result that IRIS could do in just 2 training iterations. And cart poll is a little more difficult because it's a continuous action space in a physics environment. So I ended up rounding up the inputs to 3 decimals just to constrain the size of the rule base that it learned. But it was able to complete the challenge of balancing the pole after only 32 episodes with very consistent results after that. Compared to another paper from 2020 about balancing the cart pole using deep Q learning. And you can see that it takes longer and it has much more inconsistent and noisier results. So in conclusion, IRIS has a lot of key advantages over current machine learning. And it's not just IRIS, but any type of this reinforcement or experiential learning system has these key advantages, in that it never stops learning and it learns a lot faster. The rules and the data that it is fed can consist of integers, strings, booleans, pixel values, anything that it needs to be. The planning algorithm is completely separate from the learning. So it can be anything, and you can even modify it or swap it out during runtime, or have multiple tiers of planning algorithms running in parallel, which also allows the goal to be changed at any time. So it can learn any number of tasks in an environment, and it can easily switch between them. And also, this is very important, it's that every operation is completely transparent, and it can be logged and debugged just like a classic human written program. We can see exactly how it's doing something and why. And we can see its motives, what predictions it's making, what rules it's using, when and how it learned those rules, and anything else that we may want to know about what it's doing. And it should be compatible with any environment that we put it in. So lastly, this is a video of what it looks like in action. This first clip here is of IRIS learning how to play the Grid World puzzle game. And you can see just how quickly it learns how the game works and what it needs to do to be able to solve the levels. Because this is all just one single continuous episode. As soon as it beats a level, it just goes to the next one. And driven by its curiosity and its causal reasoning, it's learning how new objects and levels work on the fly, how items that it picks up can affect other objects, reasoning about how to use those items to complete the levels. And this kind of puzzle game is not something that reinforcement learning could do, even in millions of training episodes, because it would have to be trained on each level individually over and over and over again. And it would lose all of its capability when presented with a new level. And in some of the harder levels, the rewards from collecting the battery is just too far away or too sparse for reinforcement learning to figure out what to do. Whereas IRIS isn't trying to learn what actions are the best to take in a given situation like reinforcement learning. It's actually learning how its actions affect and the world around it. And it uses that kind of causal understanding to reason its way to a solution to any given situation, which makes it a very unique, I accidentally stopped the video, shame on me, a very unique way of approaching this type of agent operating in a dynamic and changing environment. And I'll go ahead and just let that run for a little bit while we discuss anything else.
This is fantastic. Thank you so much, Barrick. Yeah, I happen to live in a dynamic and changing environment, so having agents that can handle that kind of situation is fairly important. As Patrick said, robots collecting garbage, they're going to run into the oddities. You know, we've had enough challenges just dealing with the long tail problem of self-driving cars, where you've got lines on the road and stoplights and crosswalks, and you know, a robot picking up garbage on sidewalks where we don't have any of that information is already enough that can stump the reinforcement learning systems, especially if you don't have masses of training data, right? When we are training the Minecraft type agents, again, from Alexia's example, which is just what I'm most familiar with, you need either to have the agent just make mistakes, so many mistakes, or you need to have hours and hours and hours of training data from humans that it can learn on, right? So any task that we don't have, you know, just masses of training data on become just unrealizable for these current techniques. So it's so cool to look at how we can teach an agent to learn how it's impacting the world, impacting us, benefiting us, becoming a beneficial AI, hopefully, and understanding that and making action predictions.
Yeah, and it's good that you brought up the Minecraft, because I'll skip ahead in this video here a bit, because that is one of the things that we are currently experimenting with this kind of experiential learning, is a Minecraft agent that explores and learns how Minecraft works, similar to the Voyager that Alexei was working on and experimenting with last year. We're using that same API framework to do that kind of research with this kind of agent.
That's fantastic. Thank you so much. seeing the agents adapting to their changing environment, seeing how we can surpass reinforcement learning, which is the current paradigm, and seeing how these novel methods can help agents do something that they haven't been able to do before is so exciting. Now, I know that one of the issues with AI is the combinatorial explosion, right? There can be so many paths, there can be so many problems. And I see that, if your agent's looking at predictive states, is that something that you run into, or is that something that this system helps to resolve?
It's a very good question. And yeah, that is an interesting problem that is semi-resolved by efficient planning methods. So if it was just breadth first searching and experiencing all of the different things that it would just predicting out in random directions and going on forever, yeah, that's a very quickly a combinatorial explosion. But that kind of explosion is restricted down when you have something like that dynamically calculated goal heuristic that guides the agent towards predicting towards a particular objective. And so it narrows the space down of what it works towards until it either reaches its goal or it encounters something that it's curious about. And it's like, I don't know what that is. Is this something that I've experienced before? No? Okay, well, let's see what it does or how I can mess with it. And maybe I can learn something that can help me to continue on and make better predictions in the future.
Certainly, we're missing curiosity in our current AI techniques. So this is amazing to see this being built in. So thank you very much, Barrick. I am going to move to the next. If community has questions, please feel free to post them in the comments. We'll bring them in and try and answer as much as we can. At the end here, we'll do a Q&A. So Peter, could you walk us through a bit of Metanars?
Right. Patrick, would you share? Okay. Right. So here we're going to explain and show what is Metanars on a very high level because of the time here. And then it will be followed by the NACE. So it's both of them can be fitted, and the Metanars can be fitted into the examples of the experiential learning, which it learns in the real time with the uncertainty estimation. So let's go Metanars. Next slide. So what is Metanars? What is NARS? So NARS is a general purpose reasoning system which was proposed by my advisor, Dr. P. Wang. And the Metanars is the basically NARS implemented in meta language. So it follows the generic NARS model of intelligence, which shares the paradigms such as, in particular, Non-Axiomatic Logic is a term logic with uncertainty estimation, and also features the real-time learning and reasoning, which is the most important for experiential learning as well. So Metanars conforms to the assumption of the insufficient knowledge and resources, which states that basically assumes that the resources are always finite, no matter how big the computing power is, it's always finite. And as well as system also has to be open for the new events or the new tasks at every single time, so always. Another thing is that all the reasoning and learning has to happen in the real time, and then thus it has to be a real-time operation. So can we go to the next slide? And those assumptions are really stressed by design of the Metanars. Here I want to emphasize some code structure because this is about meta as well, just to show how flexible and elegant the meta language is. So Metanars has a distinctive and efficient structure. It's modular by design. It's a very practical approach, and it's very easy to integrate and support. So you can see on the right most, it's a Metanars reasoner. Over there, it's a complex, practical, high-level, and semantic reasoning system. And it consists of the three main components. Like any reasoning system should have the logic, the memory, and the control. Each of them are found in the respective meta files. Of course, each of them has a subdivided meta files, like logic has a truth functions, like control has declarative, temporal, and procedural. But important thing here, which is innovative for the AI and AGI society in general, is that this is a modular design. which is in the future, for example, currently it's using the null logic, as I said, but in future it can use a different type of logic, PLN, for example, as a basically plug and play. And this brings the system to another level. It's basically can function as the universal control for reasoning systems. That's what it is. So we also have a modular attention allocation control, and we can switch to between different attention allocation and biases, defining different meta files. So this is thanks for the meta files and for the meta language, and how we were able to engineer it to be a very modular structure, which is very unique in the AI community to have a complex reasoning system as a modular as it is. Can we go to the next slide? I just want to show how it's written in Meta, the logic in particular. Here, you see this is not an example from the textbook. It's not like pseudocode. It's actual implementation, how elegant it is. So this, you can see the definition of the inference rules. So everyone can read them. You don't need to study the language or to understand many computer science terms. And below you can see that implementation of the truth functions as well. So this is how elegant Meta, and this is why we chose Meta to start to do the practical reasoning systems in it. Can we go next slide? So now let's speak 1 minute about architecture. So Metanars learns from the event streams in real time without any interruption. So it's always open. It extracts sensory motor contingencies, and then later it uses them to plan ahead and reach goals. So it has a decision-making mechanism as well. So Metanars is also enhanced autonomy of intelligent agents. Now this is the architecture of it, very high level, and you can see at the core we have the concept memory, basically the system memory. So it consists of the concepts. It has a long-term memory, it has a short-term memory, working memory, attentional focus, all types of memories that are registered, or different types of memory. But as well, it has them multiple controls. So it has a declarative semantic controls, where we apply the null logic and the shared terms between the premises. So it has a temporal control component, which makes the reasoning between the events which span in temporal distance. So there are no terms applied, and there is a procedural component of the control, which makes the procedural inference working. This is about the operational decision and planning. Next slide. And here we try to do some applications of the Metanars, and we applied it to the robotics. In particular, we can see here an example of the hybrid system. So Metanars here in the middle is basically no more than a ROS node, and it's connected to other ROS node, very well integrated to the melodic, very well to be supported. So it has 4 other ROS nodes like vision, distance, localization, and the gripper. So both of them supply sensory input channels to the Metanars, and as an output, based on those sensory inputs, Metanars provide some reasonings, and the output of the procedural control is they go forward, go backward, right, left operation, and the peak or the drop. In particular, the bottle or the trash or something there. So we use the YOLO V4 as the object detector, and we directly using the NARS truth values and formal language, we directly send this information to the NARS. Can we go to the next slide to see the video about this? So this is short example of the garbage collection mission. So whenever we try to first create a map, then go to the checkpoint, and that's all operated by the NARS. This is how general it is, written in Meta in the functional language. Then it tries to locate a object. In this case, it will be the bottle, and it tries to pick it up. It picks it up, and then we have established the goal, bring it to the human. To me, basically, now it will pick it up. If you can maybe fast forward a little bit. Yeah, it's now located the bottle, so it's locked it in. See, it's locking it. Now it's implementing the goal. And this is where experiential learning also captures is that, not every time you can pick up the bottle by multiple different situations. So the bottle might not be up straight, or it might be glued to the surface. Many things could happen that you simply cannot really pick it up. I mean, infinite number of ways you cannot do this, and machine learning or other systems will always attempt to do that, like we've been comparing with other systems. They would not be able to update the current belief state and current memory states, so something is wrong. They would not be able to produce some like negative evidence or some negative feedback, such that maybe we need to stop picking this up and move forward and go to the different direction, to the different location, or maybe apply a different operation to it. But you can see NARS will handle this very well. It will try to pick up, it will attempt maybe 2 or 3 times, but then it will learn that that it has more negative evidence than the positive evidence to pick the object up. And as a result, it will stop doing this. It will just go to a different checkpoint or a different place. And it will also learn that not every single bottle can be picked up as well. So this will update its entire long-term memory as well. So that's how it fits really experiential learning and that real-time reasoning in this context. I think that's it. This is a short demo. We need to go to the NACE. Or any questions?
No, that's awesome. Thank you very much. I actually very much look forward to having a picker-upper arm on my Roomba that can clean the rear end vacuum. It'd be great.
And if you can reason on the feedback of your arm as well, because sometimes you can pick it up and that can fall out from it, right?
Mm-hmm.
Or it's delicate, or it needs to go in this place, or it's garbage.
Exactly. Something NARS deal very, very well with on a high level, honestly.
Yeah, it's so important. As an AI hobbyist developer working with LLMs, it's continually frustrating how you can't update their training data, right? They're stuck, right? You know, generally or potentially with information that's a couple of years old, and getting fresh information is difficult and requires extra prompts or fine-tuning, which is not necessarily accessible. And so you just kind of have to work with what's there, and having something that can learn in real time, actually learn in real time, not just have a token window that it's kind of keeping in memory for a short time, is amazing. I do have one question that I'm just curious about. With the intention to have the robots have an interconnected memory as well, so that when one robot learns something, that translates to the other robots in its network as well?
That's a very good question. We've been actually in the past having systems interconnecting with each other, but there is a problem to the degree of belief. So how can you really be, because all of the beliefs in the current systems are true to the current experience of the system. So whenever someone tells you how are you going to believe to that? Does it apply to your situation or not? So there are some threshold can be established, and we've done that in the past, such that could be like shared memory. Or maybe it's even better, like the reasoning system can be on the server or in the cloud, controlling different robots. That is kind of, we also experimenting. By the way, where this robot currently have a 5G connection. So and the reasoning system is really runs on the server. Wow. And we can even switch between different reasoning systems, like we have multiple implementation of NARS. So and this is will be the next path toward what if we can connect multiple agents to the same NARS, like to have unite single memory, long term and short term as well.
I think that's one of my most interesting things about Hyperon and the meta language and the whole distributed atom space of all of these different systems, is that kind of a shared repository of knowledge will be possible with the infrastructure that we're building. And we'll be able to have agents that can query the whole entire hypergraph of knowledge to say, hey, I'm in this situation, what do I do? And from the experiences and all of the different algorithms that are out there in Hyperon, it will be able to return relevant information that the agent will be able to use to adapt or perform in that unexpected situation.
I agree. And there's also this interesting aspect which Peter actually touched upon, which is if you want multiple robots to share knowledge, it of course works better if the robots are more similar to each other. For instance, if there is a clone of this robot, like the same robot again, it will be able to use most of the knowledge of the other robot. While if it's a different robot, only some of the knowledge might be applicable because the physical capabilities between the robots might be different. So there's also then this question like how to make this agent exchange knowledge, and to some degree this reasoning system we have allows the agent to realize which knowledge is applicable and which one is not applicable. So differently than traditional expert systems, the knowledge does not need to be perfectly reliable because of this evidence updating mechanisms. The agent can notice by itself which knowledge actually works and which one might not work.
I think for me, we were talking earlier about the AGI 2024 conference, which is coming up in August. 13th or 14th. I keep switching my dates. So registration's opening shortly. Everybody should definitely attend. But my excitement, what I love about the AGI conferences is they're super technical. You know, we get to really dive into the logic and the math systems, meta programming, data science, all these components that are just fascinating. But it also always comes back to almost our very human experiences. Like I can try, anybody who's raised a child, I can try and tell my son what I've learned in my life about, you know, but how much will he trust that? And he needs to try it for himself. And how much does that translate to his life or to his size currently as a young person? And this is the same thing that we get to look at with robotics as well, and AI systems. And I guess I wonder if we can't have perfect trust between AI systems, where can we have perfect trust? They should be able to recognize when something is trustworthy, I guess, or be able to share openly in a way that perhaps humans aren't always optimized for. But it's a fascinating topic to look at that. So thank you very much for diving into that. Let's dive in, Patrick, to our NACE and tell us a little bit about this project.
Mm-hmm. So this is essentially an attempt to combine the best of like the AIRIS system Barrick has presented and also non-axiomatic reasoning system into one single decision-making agent, learning and decision-making agent, which can learn causal relations robustly even in environments which might be non-deterministic, like some relationship in the environment might be hard to model by the agent, or there might be some consequences which might not always be replicable. And so we essentially try to replicate also the robustness which can be seen in animal kingdom, where animals don't just learn over long time periods, but can essentially very quickly pick up very complex skills and then apply them in complex environments. And here, for instance, you see examples where a bumblebee was trained with a form of imitation learning, was able to learn how to put a borer into some place to get honey. And here there's still a debate: is this actually a form of causal reasoning or not? But there are other animals like corvids for which causal reasoning capabilities are very well documented. And for us, there's this big question: how can we actually replicate this efficient real-time learning and this causal kind of reasoning and planning, which is so fundamental for the natural intelligent species which we find in nature? And so there's really this question for us how to replicate this, and I think we have made some really profound progress in this direction recently by taking causal relationships into account and by having agents which can actually plan and reason yet learn from data. And so essentially what we want to have is real-time learning from observation, and this learning should continue. It should be incremental, and it should essentially come from the interaction of an agent with the environment. So there is no predefined data set, or there is not like unlimited training simulation steps you could perform. On the contrary, in the real world, the robot might only have very limited battery power, and it might also be that many actions it can perform might be fatal. If it makes some stupid mistake, it might be damaged. And so there's this big question: how can we actually reach data efficient real-time learning? And I think we have what it takes to show that actually learning causal relationships is exactly what it's needed for this kind of capability. Can you still hear me? Because somehow my sound dropped off.
I can still hear you.
You sound fine. Thanks.
Good, that's good. So we want the agent to learn causal relationships in the environment, and then to use these causal relationships to plan ahead and to reach different outcomes, as Barrick presented. And at the same time, we want to have this happening in a very robust way, because data can be ambiguous. There can be cases where some behavior, for some unknown reason, might not work. And so the agent needs to be able to learn in a robust way under these uncertain conditions. And so what we want to give the agent is essentially this efficient learning ability. And in the machine learning community, it's well known that there can be inductive biases, and that inductive biases can boost learning efficiency a lot, by orders of magnitude. But we go even further. We embrace inductive biases, because many of these inductive biases are not at all domain specific, but they represent wider capabilities which intelligent agents need to have in order to learn data efficiently. If we look at the cases like with the crow, when the crow learned to perform these tasks, it already had a very profound understanding about the space, three-dimensional space, how to move in three-dimensional space, how to operate in this kind of environment before it learned the concrete task, before it learned to do specific things in the environment. And so we embrace this cognitive inductive biases which allow the agent to do this. So it's fine if the agent is born with some kind of innate abilities which allow it to get around in three-dimensional space. It's also fine if there are some capabilities which allow it to learn knowledge, causal knowledge from the beginning, which it can then use when it can effectively learn causal knowledge. It can essentially use it and plan ahead with it. So we try to capture different inductive biases in the system, which allows it to easily see when something changes in the environment locally in time, then to be able to form causal relationships, to build hypotheses, and then let evidence accumulation decide which hypotheses actually are more reliable than others. And also the agent needs to be able to model the states in the world which are outside of its observation window. So we want to design agents which can do this, which have a spatial understanding, which can track things which are outside of its observation window, because only then the data efficient learning we are looking for will ever be possible. And here we have a very basic architecture where we combine these different capabilities, or we have essentially a proof of concept which shows these principles working. Essentially, you have some kind of world, and you get observation from the world, and then you build rules according to what changes in the environment, the changes you notice. And you also want the agent to notice when it makes a prediction, and the prediction does not turn out to be true. It's not confirmed by observation. It should have its attentional focus at the changes and prediction mismatches, and build hypotheses based on this. So that's what this agent does. And once it has causal hypotheses about how to affect the environment with actions, plan ahead, or how to predict the future when certain actions are taken. Then we can talk about planning. Then it's a matter of finding action sequences which lead the agent to learn more about the environment, or to maximize some, or to get reward, essentially. And that's also a key principle here, that this agent, we want curious agents. We don't want agents which stumble around via with millions of iterations like reinforcement learners. We don't want that. We want causal learning agents which systematically learn more about the environment by taking the causal knowledge it has into account and planning for potential futures where it anticipates to face the most uncertainty, so that it can learn more about the environment, so that it can build hypotheses capturing what it does not yet know. So essentially we want curious agents which explore the environment and which play with different objects in the environment, so that they can learn how to achieve different tasks in the environment. This is before any reward is given to the agent. And then, okay, if the agent has learned some basic causal understanding of the environment through systematic experimentation, planned intervention, essentially, then the agent can use this to achieve arbitrary objectives which we give to the agent, and which we can also do via reward, essentially. But in the moment when reward can be extremely sparse, but this agent does not need reward to learn about the environment. All it needs is causal knowledge, and to see when this causal knowledge fails and when it works, so that it can learn to act in the environment and can bring about different outcomes. And only then, if it already has established understanding about the environment, if it has this causal set of rules, then it's easy for it. When it gets reward, it will only be a matter of associating this reward with the conditions, and then it knows, that's how I can bring about the conditions. So when it wants to get reward, it will next time already know what to do. So this agent builds hypotheses in the environment, it plans ahead, and it explicitly tries to maximize, or to find ways to challenge its own knowledge by planning for futures where it's most uncertain about. And when it knows a certain futures bring it reward, then that's essentially what it will do via this planning process. And we can see this. We have crisp mathematics here. It's essentially a model of curiosity which captures under what conditions the agent is curious. So we have a mathematical model about curiosity, which works with this causal knowledge representation. I will not go too much into the detail here, but the idea basically is, if you have some causal knowledge and you want to apply it in a novel situation, then the basic idea is, how well does this causal knowledge actually match to the new case? Does it match very well, or is the situation a bit different? And dependent on this estimation, you get different match values, and then you can have the agent planning for future states where essentially there's more uncertainty because the knowledge it has does not match well to that situation. Here is one example which makes this play out in a concrete setting. Imagine the agent is here represented in a grid with an X, and imagine there are these bars here which represent wars, and maybe the agent already has some knowledge about what happens if there is an X at a certain location and there is an empty cell right to it, and then it goes to the right. Then the X will turn into an empty cell because it has moved to the right. And similarly, if there was an empty cell and there was an X to the left to it, then when going right, the empty cell will be the X because it essentially moves from to the right. And you can see here an example how this plays out with the match values which lead to the curiosity, which are fundamental to this curiosity model. It explicitly tries to make happen uncertain futures, and in this particular case, it will make the agent want to run into the war just to find out what will happen when this is actually happening, because it might already know how to move in empty space, but it does not yet know what happens when this X interacts with a var. So it will essentially follow the planning tree here, which leads to this collision with the var, which leads to the highest uncertainty. So it will then, once it faces the var, it will get new observation, and it will notice, okay, I cannot go through the var, and will learn additional causal knowledge in order to model this. So it will not be curious about running into the var anymore. And the evidence updating is relatively straightforward. Whenever a hypothesis predicts correctly, we attribute positive evidence to this hypothesis. Whenever a hypothesis predicts incorrectly, so is not confirmed by observation, we add negative evidence. And the total evidence is simply the sum of the positive and negative evidence. So essentially, we use simple evidence counting principles and allow the agent to build relations, but we avoid combinatorial explosion by making the agent focus on changes and prediction mismatches. So it's extremely data efficient learning, but also very targeted in a sense, or very focused. And here you see different scenarios of the agent learning different tasks. Like here it learns to play soccer, and then initially it just pushes things around how to push things, and it just pushes them because it's not sure what happens. What happens if I push the bar? What happens if I push the bar to a bar? What happens if I push the bar to another bar? And so on. These are all different futures where it's uncertain about, so it tries to bring them about until at some point it notices when you push a bar into the gore, there is some reward value it obtains. But by then it already knows how to push bars into the gore. So from there on, so here now it's trying, you see, but next time it already knows, so it does it right away because it already has the causal knowledge which is necessary to do this. And for reinforcement learning, this is extremely difficult if you have bars spawning at random locations. Maybe for this agent it doesn't matter because it has the inductive biases for it to deal with Euclidean space. So it already has this. It has what it takes. It has what it takes to support efficient real-time learning, essentially. And you see here different tasks here with a door where it has to pick up a key, and then some key counter increases, and then it has to figure out can it go through the war? It will again be curious what happens when interacting and when the key has increased. And later, when it runs into a battery, it might get reward. And next time when it sees a battery like here, it already knows, okay, I have to pick up the key, I have to use the key to go through the door and to pick up the battery in order to get additional rewards. So that's what it does. And here you see a different tasks where it has to bring eggs to a chicken. And it only gets reward when the egg is actually brought to the chicken. But when it's curious to do so because it has like an egg counter and it's a new situation. It wants to know what happens when walking to the chicken when the egg counter is 1, and then it notices, this leads to a reward. So very basic causal knowledge essentially, which then makes it realize and complete the task before other eggs in the environment. And here further down is an example which is interesting from a reinforcement learning perspective, because here you see there are electric fences. And initially it bumps into one electric fence and it gets negative reward. It does not repeat that mistake. Try that with reinforcement learning. There's no way, because first it doesn't have the inductive biases, it will need to learn it for different locations, and it will also need multiple scenarios, usually orders of thousands and if not millions, to learn this from this observation array. And you see, so here now it starts. You can see it's like collecting salad, since collecting salad is rewarding. But here it runs now into electric fence. It gets shocked, but it does not repeat that mistake because it has the causal knowledge, which says running into electric fence gives me negative reward. So it does So it avoids it in all future situations. So it's a bit counterintuitive, because in reinforcement learning we often want agents to explore the environment exhaustively almost. We want them to find the optimal policy. But here it's different. There are certain things we don't want the agent to do because it could compromise its entire existence. If the agent does something really stupid, it might die. That's the reality animals face in the real world. We cannot always find the optimal policy. It's much more about survival and data-efficient learning, which this model tries to replicate. We also have examples like in the meanwhile, we have quantitative comparison results where we can really show that these inductive biases and causal learning mechanisms lead to learning efficiencies which are orders of magnitude higher than for state-of-the-art reinforcement learning agents, at least for discrete world environments. And of course, there's a lot of work ahead of us to extend this to continuous and three-dimensional spaces. But the principles are solid, and they are necessary, we would even argue. That's one case, and I also want to show one brief live demo where we can essentially define objectives to the agent. So essentially it runs around now, it bumps into objects, it does not yet know what is the consequence of bumping into objects. So it just bumps into them, interacts with them. Here, for some reason, the cup changed location. And the goal we set is that the cup should be on top of the table. And so now it tries to realize this goal and pushes the cup to the table. But what if now we say, the table should be the cup should be below the table. Let's see what it will do. We will see. It now has a different plan. And will push the cup below the table in this case. Because now we said the table should be above the cup. And you see here this meta representation, which explicitly tells it the table should be above the cup. So that's already a combination of Metanars with this new agent, because we are striving to combine the best of both worlds, where we can have this sub-symbolic reasoning, data-efficient causal learning, but also have the high-level representations, which are useful to define high-level objectives. Like here, of course, we could also switch it around again. We could say the table should be below the cup. Yeah, but you get the idea. You can essentially change the objectives, and the agent will try to realize them. And that's essentially all from our side. But I hope I was able to give you a good overview of what it is we are trying to achieve, because we want causal real-time learning, essentially, in a very data-efficient way. And ideally, the agent should not only learn data efficiently, but in the end, which is work in progress, we also want to be able to change objectives at runtime, so that the user can tell the agent what it should do, and it can then accomplish the tasks in the environment.
It's fantastic. Thank you very much, Patrick. Thank you, Peter. Thank you, Berik, for all this sharing. I think all these demos, all of these projects show just how complex the problem of AGI is, right? It never looks easy, but when you look at this, you start to see the details of why this is such a puzzle, why it's so much more complex than the 3 months the original researchers gave themselves to develop thinking machines. And we see the LLMs. I keep going back to the LLMs. It's such a great baseline for everybody. It's what we're so familiar with right now beyond the AGI research community, and they are so impressive. As are the bots that have already beat the world chess and Go champions. Right, these are incredibly impressive, and it's funny to me always to look at what we thought are hard tasks for machines. We thought, humans will always be able to play better chess than a machine. We have the creativity and the knowledge, but we thought that driving a car, like, oh, we'll replace truck drivers. It's just driving. An 18-year-old can drive a car. Any 18-year-old in the world can drive a car, and it turns out to be the harder problem. That generality, that ability to learn in real time, that ability to anticipate the consequences of actions and not crash before it happens instead of needing to crash repeatedly to learn the problem. Gary Marcus is fond of the example of the self-driving car that was summoned on the runway and hit a plane because it had no plane training data, right? And this is infinite. There's how many planes do we need to crash cars into to teach cars not to hit planes, right? The answer should be zero. And this is what we're aiming at with general intelligence and this causal learning, experiential learning, planning, understanding the environment, that an object is solid and in front of you, don't hit it, not just don't hit a grandmother or a train or a car that you're used to seeing on the road, or could be on the road. So I find that very, very fascinating. And then, of course, I'm so inspired, Patrick, by this exploration of how do we build a system that thrives in curiosity and uncertainty. As humans, if all we do is what we already know how to do, we don't progress, right? We as humans need to thrive in curiosity and uncertainty. I certainly want to work with people that thrive in uncertainty and in what's unknown and exploration, than with people who are only comfortable doing what they already know. LLMs are useful to the extent that they're useful, and they contain a great deal of knowledge, but they don't thrive in uncertainty.
I agree. And I would even go as far to say that curiosity, uncertainty, and causality will be the three cornerstones to allow AGI to happen.
Perfect.
Figure it out.
Yeah, you heard it here, folks. We've got the basic principles, and like the Wright brothers, we're now prepared to just make the plane that meets those principles and achieve AGI.
And not
I wanted
crash
to
a car into it.
not crash a car into it. I wanted to look. Somebody in the chat gave kind of a summary. The system should be able to abstract a specific situation into a more generic one, and then it can be reused, so then it doesn't have to rely on a specific robot. This is from the Artificial Intelligence channel. Does that sound accurate, or is there anything that you all would add to that statement?
Yeah. I would say that that level of abstraction has to be done, especially for things that are outside of the agent's particular influence. So yes, depending on what kind of gripper you have, or a hand or a claw or something, that changes how you interact with the environment. But there's a lot of other stuff that goes on in the environment that doesn't really matter whether you're a robot, a human, a bird, a dog, whatever. That kind of general knowledge of seeing other things that are happening and being able to abstract those things out and share that across multiple robots, so that it doesn't really matter what type of robot that particular one is or what body it is in. It can look and say, oh, there's a ball on an incline, it's going to roll down the hill, and be able to expect that kind of interaction in the real world is going to happen.
Right. I can just add to this, absolutely, but that's why I mean, none of those systems represent an AGI, complete AGI solution, but the hybrid system does, may at least may try to do this. And that's where we look at that adding the semantics to those sub-symbolics can really help us reach and abstract the knowledge what's learned in the sub-symbolic efficient way, bring it to the higher order of reasoning. We think is the key for the future, for the AGI actually. Because it's impossible to engineer a single system to solve all the types of problems in the same doing in efficient way.
Thank you very much. Yeah, and thank you for
There is
bringing that up.
also, I'm sorry, there is also a question for Patrick, if that NACE is motivated by any causality theory or what. I think not, or Patrick can respond, and if not, I can add to that.
Yeah, it's not following Choudhry Bull's work. It's following Pei Wang's work, which is fundamentally different because it says a causal relation, even though the agents should strive to find causal relations, the knowledge it has is not necessarily causal. And it's not like in Bull's work where you have a causal theory, you have a causal graph, and then you make inferences based on that. And with intervention, after intervention is performed, you end up with different probability spaces. It's not like that here. Here, the causal knowledge is really obtained from correlation, but from correlation which involves own action. And that's the key difference. The agent acts in the environment, and it gets observations which have to do with the actions it took. It is in a certain context, it performs an action, and then it makes new observations, and it forms this kind of procedural knowledge with evidence updating based on this interactions with the environment. So it's relatively mathematically, it's not that complex actually. But it's fundamentally different than Bull's work because it is essentially learning from correlation. Correlation is all there is essentially in this model. It doesn't need more because it will see which of these procedural knowledge pieces, which of these causal knowledge pieces will actually work or not, because it can try it. It can try it and see, does it actually lead to the consequences it wants to achieve? So it essentially is an empirical reasoning system. It's purely empirical. It does not need a causal theory to exist beforehand, or it needs this evidence updating based on interactions with the environment.
Thanks, Patrick. Thanks, Mike. Great to see you here. Great question. Great answer. Does anybody else want to chime in on that question?
I would say that, at least for me, it's not about any particular theory of causality explicitly. It's kind of more just a general self-inspective reflection on how I learn things and how I see the environment, and how when I'm playing like a new Atari game, when I was a kid, I had an Atari and then play games, and I'd have to understand and learn how the game works. And every game was similar but different, and so different games that looked similar would have different rules. And it was only through that experimentation that we can learn how types of games and new experiences in general work, and how we can do whatever it is that we want to do with what we're interacting with. And I think that that's really the key. Like Patrick said, is that curiosity is key, and the predictive modeling is key to be able to have that world model that it can have inside its head. It's an imagination. that view of NACE that Patrick was showing, where he was demonstrating that his character moving around, that was us peering into the agent's mind and seeing what it's thinking and what it's planning and what it's going to do. And that kind of transparency just doesn't exist in current reinforcement learning or other types of machine learning. So especially from like a safety perspective, I think that that is a fundamentally important feature of these types of systems.
Yes, thank you very much, Barrick. It's so true. Being able to understand how an AI is making a decision, making a choice, and acting in the world, and being able to intervene even and give it very specific information if needed to help it act in a more beneficial way is so critical, and something that's completely missing in the sub-symbolic area of neural networks. Doesn't seem like it's going to be an easy add-on if possible at all. So yeah, thank you. Well, we're over time. I thank you all very much for being here. It's so exciting to hear all the ways that AGI is in development, the ways that um, there's this massive cross-pollination of ideas and projects and directions that are coming together in the world, in OpenCog, in Meta, beyond OpenCog, beyond Meta. As you guys were all pointing out, creating these modular, interoperable systems where different types of inference and logic, causality models, prediction can all be combined, can be tweaked, can be adjusted, can be interchanged until we find something that really gives the best, most general intelligence that we're able to give. And I hope at that point that the computer, the AI, can take over and optimize itself from there based on its own understanding of how all this works. But to get to that spot is our current challenge. How do we design something that can think well enough to recursively self-improve its own programming? Thank you very much for being here, for presenting. We have GitHub repo links to NACE, to Metanars, to AIRIS. Barrick, Patrick, Peter, it's been an absolute pleasure. I want to remind everybody, keep an eye on the AGI conference site. Registration's opening shortly. That's going to be August 13th in Seattle, Washington. And then if you are interested in attending, if you are an AI, AGI-ish researcher, workshops, tutorials, demos, proposals are due on the 10th on Friday. So get those in. All the information's on the website, agi-conf.org/2024. And we look forward to seeing everybody there, either virtually or live, and we'll see you again soon.